Dear students, in this video we are going to study one theorem related to the complete graph. Okay, so we in previous class have seen the definition of complete graph. So complete graph at least needs three edges and three vertices, and every vertex is connected to remaining vertices. Okay, so this is a complete graph where there are at least three vertices and every vertex is connected to remaining vertices. Okay, so this is called as a complete graph. So what this definition tells, this theorem says that complete graph with n vertices consists of n into n minus 1 upon 2 edges. So we have to prove this, that the number of edges in a complete graph where n represents the vertices, so number of edges are equal to n into n minus 1 upon 2. So solution is like that. So we are considering loop free complete graph. So obviously the complete graph we are considering here loop free, there is no presence of loop. Each vertex is connected to remaining n minus 1 vertices. So if you take the example of this vertices, that is this vertex 1, vertex 2 and vertex 3. So there are three vertices. So this first vertex is connected to two other vertices, that is vertex number 2 and vertex number 3. So 3 minus 1, that is n minus 1 vertices are being connected by every vertex. Okay, so 3 minus 1 is equal to 2 vertices are being connected by every vertex of this graph. So every vertex is connected to n minus 1 vertices. So degree of every vertex is equal to n minus 1. So degree of vi is equal to n minus 1, right? So we already know that the summation of degrees of all vertices of a graph is equal to twice of edges of the graph. Okay, this is the this is the handshake lemma. Okay, this is from the handshaking theorem. Okay, so the summation of degrees of all the vertices of a graph is equal to the twice of edges. So this is handshaking. This is from we have taken handshaking theorem, right? So as we know that there summation of degree of all vertices. So in complete graph, a degree of a single vertex is n minus 1. So n minus 1, n minus 1. This is up to n. So how many vertices? N vertices. So that is equal to twice e. Now n into n minus 1, because there are n such vertices, every vertex is having n minus 1 as a degree. So this is n is the number of vertices. So this n represents vertices. N minus 1 is the degree of vertices. So is equal to twice of edges. E is the edges. Okay. So if you take this 2 on this side, you will get the formula that number of edges is equal to n into n minus 1 upon 2. So this is the formula of this theorem. We have proved that the number of edges in a complete graph without a loop is equal to n into n minus 1 upon 2, where n is the vertex of a graph, n is the number of vertices in the graph. Okay, so we'll prove this. Now let's take the example that suppose there are 4 vertices. So the complete graph you have to draw. So this vertex, that is vertex number 1, should be connected to every other vertices. So this is 1, 2 and 3. Okay, so we will call it as vertex A for simplicity. Vertex A, the degree is 3. Okay, now take the example of vertex B. Vertex B is being connected to every other vertex, that is these vertices. Okay, this vertex C and let's say vertex D. So each of these vertices is having degree 3. So you already know the definition of degree of vertex. This is also having degree 3. So and calculate the edges in this graph. So this is H1, H2, H3, 4, 5 and 6. Okay, so 6 edges are there. So if you calculate this formula, E is equal to n into n minus 1 upon 2, right? So number of edges is equal to n. How many nodes are there? 4 vertices. 4 into 4 minus 1 upon 2, that is 4 into 3 upon 2, that is 12 upon 2, that is equal to 6. So number of edges, the number of edges in this graph is equal to 6. So we can prove that in this graph the number of edges are 6. Okay, so hope you understood this theorem. Theorem is that show that a complete graph with n vertices consists of n into n minus 1 upon 2 edges. Thank you.